Hello everybody, this is our team and today we will be presenting our DevOps continuous development pipeline that we implemented over the course of the semester. In total, we had 4 major milestones. This provides a complete overview of the project. We can see how different components were added incrementally to the pipeline during the milestones. Milestone 1, Configuration Management. In this milestone, we set up build environments for 2 software projects using Ansible as the configuration management tool. The first application is a Java application called iTrust. We provision the server with MySQL database, Maven, Git, and Tomcat to run and build the application. The next application is a Node.js-based web application called Checkbox.io. The server was provisioned with Git, Node Package Manager, Nginx Web Server, and MongoDB. Checkbox and iTrust were provisioned on 2 VMs by running Ansible scripts from a host machine which already had Ansible pre-installed. Milestone 2, Build, Test, and Analysis. For this milestone, we added an Ansible script to set up a Jenkins server and created various build jobs, one for Checkbox.io, one for iTrust, and one for running the fuzzing tool. As soon as a push is detected on the master branch, a post-commit script runs the fuzzer 100 times and pushes the changes to the fuzzing branch. Here on the fuzzer branch, we can see a list of 100 commits. The useless test detector utility helps identify test cases that always pass, and here's a sample report from running the useless test detector. For Checkbox.io, we implemented a simple static analysis tool which looks for simple metrics and fails to build if one of these metrics are not met. Milestone 3, Deployment. We will first run the installation of Jenkins server on the first VCL instance. We have a Git hook that will be triggered after a Git push to either the Checkbox repo or the iTrust repo, and it will be responsible to create a Jenkins build job on the VCL instance. After the builds are successful, the projects will be deployed on separate VCL instances. Checkbox.io is deployed using Docker containers as shown in the image. The application, Nginx, and Redis instances are each separate containers, and we use Docker Compose to tie them together. We also create a Redis master container and a Mongo container since they will be shared among the canary and the stable instance. We have a load balancer implemented using HTTP proxy that distributes traffic between the instances. We also have a polling agent which periodically polls and checks if all the deployed instances are running. If any instance is not responding, it removes it from the load balancer. For the final phase of milestone 3, we again make use of Docker containers. As shown here, every replica of iTrust is a container. Each iTrust container is composed of the application and the Tomcat server container. The replicas share a MySQL container connection. We make use of Docker Swarm to implement the rolling update. There is a master container node that controls the other slave replicas of iTrust. It upgrades each instance one after another with a 60-second delay. Does scaling your application aggressively increase your performance? This is the question we try to address in our special milestone. For this milestone, we focus on Checkbox.io, and we want to analyze the performance of the application when running different number of instances. At first instinct, it might appear that if we just simply scale and run 10 instances of Checkbox.io on one server, we will get better performance. However, this instinct fails to recognize the limit certain resources can pose. By monitoring the server, we can identify possible bottlenecks that might not be obvious. We reserve 2 different droplets on DigitalOcean, and one of them is called the big machine and the other one is called small machine on the table. And we can see that we tried even different proxies. On the small machine, we tried HTTP proxy, and then we tried one without a proxy. And we realized that the one without the proxy was serving more requests per second. And similarly, in the big machine, we had HA proxy, and we had no proxy, and we also had HTTP proxy. And again, the same pattern can be observed. The number of requests served per second is higher on the no proxy one. So we concluded that the bottleneck can occur at the load balancer. One interesting thing to point out is that HTTP proxy has a very poor performance, which can be seen on both the big and the small machine. And HA proxy has a very much comparable performance and is 10 times better than HTTP proxy. In conclusion, we have come to realize that a load balancer does not always guarantee an improvement in processing requests per second. When the bottleneck occurs inside the application, scaling might help. However, if the bottleneck occurs in other places such as the database, increasing the number of instances does not help in addressing the problem.